So continuing on with the same theme, to present binder and asphalt performance, I'd like now to introduce our next speaker, Jalal Sufi Sabah, airport engineer for Oricon. Jalal holds a civil and infrastructure engineering degree with honours from RMIT University. He joined the Oricon airport team in 2011 and has since worked on a range of capital city and regional airport projects. Most recently, Brisbane Airport's domestic and international apron development. So please put your hands together and welcome Jalal.
Well, hello everyone. I know at this time you probably want to get into some afternoon tea, so I probably won't be as exciting as food at this point, but I'll try to make it as interesting as possible. Right, so for the past few days, we've looked at some of the latest in airport thinking, technology, regulation, and economics. For the past few hours, we've looked at more what's right underneath our feet, which is our pavements. So with that, again, my name is Jalal. I'm an airport engineer at Oricon, and I'm going to talk to you about asphalt pavements. Now, when we talk about asphalt, it's customary to talk about definitions. So let's do that. The Oxford English Dictionary defines asphalt as being a dark bituminous pitch mixed with sand or gravel that is used for flooring, roofing, and roads, obviously. Now, other dictionaries have other definitions. But depending on your definition, usually when we talk about asphalt, we talk about what's going wrong with asphalt. So let's look at some common airport distresses that we find at airports to do with asphalt. Now, there are some commonalities across airports. We do have certain loading conditions at airports, heavier loads than, for example, that we have at roads, infrequent loads compared to roads as well. But this is what we usually find, and what has been documented has been the common ones that we find at airports. So first is cracking, more top-down, not bottom-up, that we see with roads. Rutting is also another one. We also see groove closure, very characteristic of runways, and we see moisture stripping as well as one of the others that we see at airports. Now, I've probably got to focus on one distress type. If not, I'll probably finish my presentation somewhere mid-Tuesday next week, so I'll focus on one. And the one I'm going to go for is rutting. And there are a few reasons why I'm focusing on rutting. First of all, rutting can lead to some of the others that are on the screen, can lead to worsening some of the other effects. And it can also, for example, play with your geometry. It can play with getting your taxiway out of MOS compliance, for example. It can, because of the shallow depressions, it can invite bird baths and invite birds. And because of that standing water on your pavements, it can increase the likelihood of aircraft skidding. So let's look at rutting. Now, the factors that contribute to rutting at our airports are a lot. So there are a lot of factors that contribute, all the way from design, where we have grading, all the way to, for example, if you have low air voids, too low air voids, and you can see rutting potential. We also see aircraft loads. Now, it's no surprise that aircrafts are getting bigger, more heavy, and it's no secret that aircraft manufacturers, I don't know how you manufacture an airline, aircraft manufacturers are wanting to go heavier and higher tire pressures with their main gears. They want to go higher tire pressures because it means less of a size for their main gears, so it cheapens their aircraft costs. But it has a negative effect on our pavements, one of which can lead to rutting. We also see during construction, if you're not compacting it, for example, well off in the field during construction, then you're going to be compacting it during operation, which is not wanted. And the last factor, probably one that we have least influence over, which is our environment. So when we look at, for example, solar radiation, the effects of sunlight, all the way to precipitation, the effects of water, and then lastly, temperature, the effects of heat on our pavements, and in particular on asphalt. Now, I'm going to, again, focus on something, and I'm going to focus on temperature being the major factor to rutting. And this goes back directly to the weakness, the inherent weakness that asphalt has with regards to temperature. Now, From my understanding, most of the asphalt types, if not all of them, have this inherent weakness, which is because it's a viscoelastic material, because it's time load dependent, you get to a stage where the hotter it becomes, the softer it is. And that is probably true for all asphalt types, even some of the premium stuff that I'll go into a little bit later. So let's look at temperature. Now, when I was given the exercise into looking at temperature, looking at rutting, looking at asphalt use, I said to myself, okay, let's look at some of the airports across the world and to look at also Australian airports. And let's see whether there's any commonality, any observation to be had when you look at airports across the world and how they've organically grown with their pavement use. Where have they used asphalt? Where have they used other things, such as concrete? And so this is the exercise that I went to try to do. Now, I had to come up with a climate model. This is not mine. This is the Köppen-Geiger climate model. It's pretty scientific. It leads to consider precipitation and temperature. And just bear in mind, this is not going to be an exact model. I'm going to be choosing airports that have similar climates that you may then disagree with. But for the sake of relativity, I think this is going to be useful. So starting off with our coldest relative climate in Australia, where we have Melbourne, Hobart, compares with Western European airports and the climates there, and temperature zones there. Perth and Adelaide deal with similar climates, similar temperature zones, and they compare with Concepcion, for example, in Chile, Portland in the USA, and Porto in Portugal. Brisbane and Sydney is also represented, being more of the hotter, fully humid climate types, and they compare with Buenos Aires, Colombia in the US, yes, there is, and Osaka in Japan, and last but not least, our hot desert, arid climate, Alice Springs, comparing with La Paz in Mexico. Yes, there is a La Paz in Mexico, before I get a question, and Bisha in Saudi Arabia. Now, what I've got there is basically a table where I'm going to show you some of the asphalt percentage uses at each of the facilities at these airports. So whether it's a runway or a taxiway or an apron, they are going to be some of the asphalt uses there. Now, I've already grouped these. From the top of the screen, we see more of the colder climate type, the colder temperatures, all the way to our hot desert climate right at the bottom. So you can tell that some of the absolute highs and average highs in terms of temperature, we're getting hotter as we go down the screen. Keep that in mind. Now, these are the numbers, and while there is a lot of numbers out there, what I found useful was flipping this and looking at it not from an asphalt use perspective, but from a concrete use perspective. So that's what I did. And when we do this, a lot of things start to become a lot more observable. Now, I chose concrete because there is a factor in concrete in being different from asphalt. Concrete doesn't have that inherent weakness to get softer when the temperature gets higher, if we're not talking about very, very, very extreme temperatures, which doesn't happen in surface. So let's look at the concrete percentage. The first thing that I observe is how much concrete relative to everything else is being used at our aprons. So where we have standing aircraft, that we see a fair bit of concrete. Okay, standing aircraft makes sense. There is a lot of distress from standing aircraft to the pavement. What we also see a fair bit of concrete is with our taxi lanes. So where we see slow-moving aircraft, a fair bit of concrete there. And the other one where we have a fair bit of concrete is our thresholds. Our concrete thresholds for our thresholds at our runways, where we have slow-moving turning aircraft. We also see a fair bit of concrete there as well. Now, before I get off this slide, there is also a slight correlation now between the bottom half and the top half of the screen. There is more concrete, arguably, in that bottom section of the screen than the top section. And it goes to show that when you get hotter climates and you get into hotter climates, you are probably going to see more concrete being used because, again, for that inherent weakness, and especially where we have standing aircraft, slow-moving aircraft, turning aircraft, you probably want to see more concrete. Now, again, this is not an exhaustive list. This is only a very small sample size of the airports across the world, but it does provide some indication. Now, to bring it back to asphalt, since this is an asphalt presentation, let's look at some of the emerging thinking out there. And we can start to see, because the asphalt industry has been worked on, and a lot of technology has gone into asphalt. So 12 years ago, the technical working group at the AAA came together and they started out in looking at some of the objectives that they wanted asphalt to achieve. Some of those are as valid as they were 12 years ago as they are today. For example, the first two that you see up there are directly related to rutting resistance with asphalt against higher and higher temperatures. So there's always been this concern. This is not a new issue. And it's not my presentation to give you guys, to pretend that this is a new issue. This has been going on. This is why also asphalt has developed, and there's been a lot of technology put into it to increase its rutting resistance. One of the ways we can do this is by looking at materials and design mix methods. So you probably have heard of EME1 and EME2 coming from France. Translating more to high modulus asphalt, it has high bitumen content, it has high fatigue resistance and rutting resistance, and is at the moment being technology transferred into the TMR, into Queensland at the moment. They've done a few trials. And I've also got to mention that Brisbane Airport, not that they need any more accolade, but they are probably the first major airport in Australia, one of the first at least, to have and trial EME2-based asphalt with their taxiway hotel project, which Oricon is involved with. So very exciting to see. The other place that we see innovation, and again, these are not new, but these do represent design methods and materials that push the envelope in terms of where asphalt can be. Superpave, you may be aware of it, the PG-MSCR method over in the United States. They tried to get away from some of the more traditional Marshall method to mix design for asphalt. Now, Marshall is used still in parts of the world, even in parts of Australia. But this is what they tried to do in the United States with their Strategic Highways Research Program in the 90s. Now, what's interesting about the Superpave method is the way that they classify their binder performance grades. So, for example, LaGuardia Airport, in a few recent years, they constructed and they designed an asphalt mix for one of their taxiways that achieved a PG9422. Now, PG9422, both of those numbers form the performance grade for the binder that they used, but they're both relating directly to temperature. So the 94 relating more to maximum temperatures, the 22 to minimum temperatures, but it just goes to show how important temperature is when we're talking about asphalt. And for those that are aware of the Superpave method and the PG-MSCR ratings, 9422 is an amazing, highly amazing mix, and surprised that they achieved it. The other places that we can look at, Australian manufacturers and contractors have also looked into producing asphalt mixes and binders that are pushing the envelope, so using polymers, elastomeric, plastomeric polymers to increase the rutting resistance. So there is some work there as well. Now, we don't have to just look at airports, we can look at other industries. One of the industries that I want to look at has to do with the US Cool Pavement initiative that they're doing with their urban centers. And we'll see a little bit about that. So basically, the gist of this, and to think about solar reflection, is as follows. Physics 101 will tell you, the darker the material, the hotter the material will be. That's just how it works. The lighter the material, the more light it reflects. As you can see, there's a disparity between light and dark materials. Now, the University of Berkeley did a study, did a very simple experiment where they looked at different surface colors for their pavements and then tracked with an ambient temperature of 22.5 degrees, they tracked what was their pavement temperature after a few hours. What they saw was with dark asphalt, it went up to almost 60 degrees with a 6% albedo or a solar reflection ratio of 6%, so it's reflecting 6%. When they pigmented over that asphalt with another pigment color, the solar reflection went up, but also the pavement temperature went down, which is to be expected. And with concrete, not that concrete needs to be cooler per se, but since it is white, it has that also going for it. Interesting observation, if you haven't made it already, is the dark asphalt, it's got a weakness in getting softer when it gets hotter, and yet it's got the worst possible color for combating against that. Whereas concrete, it's got both of those things going for it, color and the fact that it doesn't have that inherent weakness to softening under temperature. Now, I do want to make a note of this. The reason why they've looked into this in the US with their urban centers is because of the urban heat island effect. Basically meaning, with their urban centers, they generally get hotter because they've got more roads, more dark roads there. Their general environment in the urban centers are hotter than in their rural environments. And so they try to look for a way to cool them down because it means less air conditioning costs and so forth. So what they found from this study is you increase your solar reflection by 10%, do something with the color, and you can decrease your pavement temperature by 2 to 3 degrees. Now, what are the ways that we can look at doing this with our industry? Well, we can try to use lighter aggregate, subject to spec testing, of course, maybe limestones or white granites, for example. We could also look at is surface treatment. So in LA at the moment, they've actually painted some of those roads with a pigment to try to get them transferred to being white roads for that very effect, to solar reflect and to get those pavements cooler. Now, there's probably some concerns with this. I'm not advocating right now that we should definitely get it into your airports right now. There's probably some concerns with surface texture, such as, so MOS compliance and also skid resistance, maybe durability as well, but it's something that we could look into. And of course, aging. So as you may have found, with your aged asphalt mixers, asphalt pavements, the more they age, the fader they generally become. And so when they become fader, they become less dark, and so they would naturally reflect more light. But at that stage, you wouldn't want to seek out aging because it invites other pavement distresses. Now, I just want to give you guys a little bit of a reward for getting this far through my presentation. I don't know whether you've been given a reward before, such as this, but what I want to do is give you guys a potato. And I know this is very, very unconventional. It's a bit different, but it's actually at Oricon, we like to do things a little differently, and especially my team likes to do things a little differently. So with that, and with that compulsory Oricon plug, and now that I've passed my KPIs for the year, I can move on. So we've spoken about materials, we've spoken about different industries and looking at some of the innovation there, but we haven't spoken about what's missing in Australia compared to some of the other places in the world. Now, asphalt selection guidelines, there are asphalt selection guidelines in Australia for roads. So for example, for ELSE roads, for some of the state road authorities, we do find those types of selection guidelines. When we talk about the airport industry in Australia, however, there isn't anything there, not something that's unified anyway, especially not something that's regulated. Around the world, there are. France being probably one of the best examples of this asphalt selection guidelines for airports. And they go to mixers that are normalized against the European standard mixers. Whether Australia gets to that point, I guess is yet to be seen. To go into then some of the selection guidelines in France, this is what they consider. So they consider the traffic level. The traffic level being a function of the number of movements as well as the tire pressure and the number of wheels. So we're looking at tire pressure. It's very good because it stresses the upper layer of the pavement where the asphalt is, and it looks at the movement per day, another pertinent issue. What they also look at is the environment. All right, perfect. We're looking at climate type, and they're looking at temperature. Both things that we've already sort of looked at when we're looking at the airports across the world and the asphalt use. So very, again, pertinent to look at. And they also look at the area where you are at the airport, whether it's a runway, whether it's a taxiway, whether it's a threshold, parking position. They look at all these three factors to then come up to a recommended approved asphalt mix. So going through some of how easy it is, and this all could be replicated for Australia, but let's go through some of the tables. So for example, for the traffic class, they've got movements on one side, they've got the number of aircraft and the tire pressures on the other, and they come up with a traffic class 1 to 5. So they've got a CT, traffic class, 1 to 5. Don't ask me why it's CT. They've got climate type, so they come up with a climate type again as well by looking at the minimum and maximum temperatures. And they come up with a climate type. This, again, could be done for Australia. And they come up with a stress level that is a composite of traffic, of the environment. They get it together and they come up with a stress level for that case, NS1 to NS4. Now, with that stress level then, and with where you are at the airport, stress level at the top side, they have their recommended asphalt mixes. Now up there, I've got the base asphalt selection. There is another table for surface course, for regulatory course, but this is what it is for base. And you can see EME and EME2 is represented up there, since we're talking about France. Now, what's interesting to note that even after all of these important considerations from traffic, environment to area of application, they still caveat these tables by saying two interesting things. I'm not sure whether you can read it, but they basically say for where you have punching, where you have a risk of punching through, where you have standing aircraft, you would want to go with concrete. Don't consider asphalt with doing this. And, sorry, going back, and the other thing that they look at is for the defense airfields, where you have, for example, more risk of oil spills, or you have the heat coming out of the fighter jet engines. Because it is, again, an inherent weakness in the asphalt that it gets softer when it gets hotter, you're looking at a recommendation for concrete in these areas as well. Now, last sort of chapter of my presentation, I need to talk about practicalities, or else my presentation may be a bit short. So let's look at sort of a case. Now, we've already looked at that when you have standing aircraft, when you have slow-moving aircraft, turning aircraft, there is heightened risk, even when you're using premium asphalt types and additives and polymers. There is still that ceiling and that limit when it comes to asphalt in those scenarios, especially when you have hotter temperatures. For example, a large Middle Eastern airport, in the few recent years, they constructed a taxiway. Designers in the US, playing to the FAA latest design guidelines, went and designed their asphalt mixes. Now, within months after construction, the asphalt rutted. And it rutted in places where, especially where there was turning and slow moving. So they went back, they retweaked the design, and they found that in certain areas, they actually did away with asphalt altogether. They did not even replace some of the areas there with asphalt. They just went straight to concrete. So it just goes to show that when you're talking about, even when you have some of the latest thinking, some of the latest technologies, some of the latest a lot of funding as well, as you would expect with a large Middle Eastern airport, you are still hitting some of the issues that you may find because of that inherent weakness in asphalt. Now, I know what you're thinking, okay, concrete is all well and good, but what about the cost? And I agree with you. It is far beyond me to tell you where that decision to be made. But I think it is important to consider from a life cycle perspective, looking at concrete. So there was a case study presented in Canada about an airport in Florida, Pensacola International Airport, and what they found is they had a case study where they wanted to rehabilitate a runway intersection. They had Boeing 757s, so code D aircraft, and they had two pavement bidders. They had an asphalt bidder and they had a concrete bidder. Now, what they then wanted to do, they had the initial construction costs for each of these, but they wanted to level out the playing field and look at it from a life cycle perspective. So they chose a 20-year life cycle perspective, using the present worth calculation method for bringing it all back to life cycle costs back to today's dollars. Present worth is an FAA approved, so that's the method that they have in their advisory circular, so 150-5320, and this is what they found. Now, it is important to note with present worth, you're looking at C, which is your construction cost, M, your maintenance cost, and your S, salvage value. So inherent in the life cycle analysis, you've got to assume that at the end, you're going to salvage your pavement. This is how they bring everything back and look at the value of the pavement. Now, both of those pavements are as follows. Asphalt was designed to 30 years, 300 millimeter deep asphalt. It's almost like a full depth asphalt that you use for roads, but that's just an observation. For concrete, they had a 430 millimeter concrete for that. They went to 40 years, which is probably standard. With the 30 years for asphalt, It's probably a little bit higher than normal, but this is what they had. Again, they went back and standardized it and made it a level playing field to 20 years. Now, going through some of the maintenance for this, because it goes into the present worth calculation. For asphalt, it is probably known that you're going to have more maintenance with asphalt during the maintenance years, especially when you come up to at year 15 is what they had. They went and re-sheeted the runway, at the rehabilitation section with asphalt, and it's probably one of the major maintenance costs, as you probably are all aware. Overlays are not cheap. With concrete, they really didn't see any need to forecast any maintenance for this for the first 15 years. And this is important. Yes, concrete has an initial high cost, but for the first 15 years, you're probably looking at minimal maintenance costs. At year 20, they said, okay, they may replace a few slabs. And I think that I agree with that. You will have maybe some minimal slabs that you need replacement, but as a general, there's less maintenance. With salvage value, again, what we're looking at is it was designed to 30 years, the asphalt pavement, so they had a 10-year remaining design life. They could recycle some of those materials, so they had value that they could come out of that salvage value if they demolished it after 20 years, for example. And with concrete, with 40-year design life, again, they looked at 20-year remaining life, so obviously we had a little bit more in terms of salvage value coming out of there. Now, when they put all the costs together, I won't bore you with it, but they found when everything came down to a level playing field, when they brought everything back to present-day dollars using a discount rate of 5%, they saw that concrete was a bit cheaper. Now, that's a life cycle perspective. And it is caveated by saying, FAA does say that if you have present worth comparisons that are within 10%, then they're probably similar in terms of life cycle costs. So, okay, we can take it as being similar. However, you've got a pavement type that is susceptible, when increasing temperatures, is susceptible to rutting, to softening, and especially depending on where you are putting it in the airport, where you have, for example, standing aircraft on it, or turning aircraft, or slow-moving aircraft. These present an inherent risk for that particular pavement type, which is probably the asphalt. And you have another pavement type, similar life cycle costs, but yet you don't have that worry of concern as much as you would for asphalt, especially if you're getting hotter and hotter climates. Now, I've just gone to that's it for my presentation. The two takeaway messages that I probably want to give you guys, please don't remember my presentation as the one with the potato, but the two takeaway messages I want you to take away is when you're looking at your runway thresholds, or you're looking at your taxi lanes, looking at your apron parking areas, especially if you're seeing hotter and hotter temperatures at your airport. It could be a volatility of temperature as well, as we're seeing with Adelaide in the past week. You would want to consider concrete, and to consider also the life cycle cost is going to be an added consideration. That's what I would recommend. And then secondly, let's looking at asphalt selection guidelines for Australia in the same way that we can base it off what they do in France, but I think that could be very helpful for the industry. So with that, I know there are very simple notions, but sometimes the simplest notions give significant consideration later. Thank you very much.